right? Hopefully you've studied a little bit leading into this. We didn't wait till right now to start ramping up. So we're just gonna do what we did last time. I'm just gonna go through these things. So it's on work energy problem and an impulse momentum problem, and it'll probably be similar to this where it's a little combination between like a impact and a work energy. Kind of like what our examples in class were, and then what this example is. Same thing, 1 page of notes. Go to the same room you went to last time. I may or may not be in that room. I'll definitely be in this room. Because this one's so much better. Look, you got windows and see the outside. It sucks to be those other people, but just be lucky. If you're in this room, just be lucky you're not one of the others. Okay. So any questions before we get started? We're doing okay? Okay. All right. So here we are. And again, just keep in mind too, that I mentioned this before, this came from COVID years and the students had an hour. So you might be like, how am I supposed to do this and the other one in an hour? Two in an hour. This one was designed for an hour, right? So I can't go as deep as I did here. This one was a little bit deeper, but you should definitely know how to do this problem given enough time, right? And if you could do this problem, you could do the problem on the exam, which I have written at this point, okay? Yep, okay, so Calvin and Tom, I did have it right here, and I was like, I'm gonna accidentally hit the solution because I had it on this thing. So I made sure I closed that one so I didn't accidentally hit that one. Okay, anyways, so Calvin and Tom again, there's a Calvin and Tom again problem. They're up here and they go whipping down and they go around a loop and they come around and they do another loop and they go around. And this is what I think is fair because you had a homework problem that was similar to this. There was like one loop, kind of a car went around a loop. So this is fair, right? So it starts out, where it adds a little bit of complexity is they start out at the top and then it says, what is the minimum height such that the cart can travel around both loops without making it around the corner, right? And make it all the way rather, okay? So right offhand, right, you could put a little bit of intuition and be like, which loop is gonna control? Like, what's your thoughts on which loop was gonna control? The bigger one, right? The bigger one's gonna control. It's gonna come down, and it's also gonna lose more energy when it goes, because it's gotta go rising back up, so it's gonna be a little bit slower. Then the radius is bigger. So my guess too is that loop B is gonna be the one that controls that, right? But if you didn't know it, I'll set it up so both ways. So if you didn't recognize that, you could set it up for B or C, and then you'll find one is going to be controlling, right? So that's what it is, right? I mean, we want to find it right at the cusp where that normal force is 0, right? And that would tell us the minimum height. And this is again similar to a homework problem you did. So let's do that. Okay, let's go through that. So this one, these aren't easy because you have to do a little FMA first, some force mass acceleration, to kind of set this thing up. That's where we're going to do a little force mass acceleration to determine the minimum velocity that they have to be at when they go around this corner. Right? That's force mass acceleration. Then based off of that minimum velocity, we'll be able to calculate what height would be required to hit that minimum velocity. Okay? Did everybody do these yet? You just wait. Did you get it? Yeah, good job. Good job. Right? The one that you may have had a little bit of trouble is this extra credit one. You might not have gotten, and we'll talk about that when we get down there. Because to be honest, the first time I did it, I'd had it wrong, and the student corrected me, and I was like, oh, right? And they were right. But I knew that I was wrong, and I was just waiting for them to correct me. Okay, so let's do that. So I'm going to start out with a little FMA. Force mass acceleration, right? And then I'll do a little free body diagram. We've got, right, mass times gravity going down. And then there would be a normal force, right? But what we're going to be solving, the key to this problem is we want that normal force equal to 0. Right? I'm going to put my coordinate system on here again. I did mine in polar coordinates, your hat. It's going that way, right? It goes from the middle and then up like that, right? So there's my free body diagram. And then I say some of the forces in the R direction. Ooh, I want that black. All right, some of the forces in the R direction. It's equal to minus mg. It's minus because it's pointed in the opposite direction, right? Mg is going that way. And the normal force is 0, so we'll just leave that out. right? That's equal to mass times r double dot minus r omega squared. If I'm doing it in this coordinate system, r double dot is 0, right? You can rewrite this and just make this, oh, I'm missing a negative out front. This would just be negative mv squared over r. That's another way of writing that r omega squared, right? And so in this case, these masses cancel each other out. If you're really just trying to solve some stuff, masses cancel each other out. And so I can get an equation over here. The velocity is equal to g times r, so 1/2, right? The square root of g times r. So again, right, I set it up right now not knowing if it's b or c the control. I haven't set that radius here. And so I could set the radius just to kind of demonstrate. You set the radius for r equals 9. Equals 9. That would give me my v min equal to 6.64.
Does r equal 9?
Yeah, r equals 9. No, r 9 over 2. R equals, I wasn't done yet. Okay. R equals 9 over 2, 6.64 meters per second. And then if I make r, I like how you asked me that like a quizzing me. Does it really equal that? Does it? Huh? Look at it. That's the diameter, you son of a bitch. Right? V min equal to 5.42. Right. So then, I mean, now, so that, again, if you didn't notice that, if you didn't deduce that, right, then you would find it there. So I can solve for both of them, right, both radii, right? And so that one's going to be the one that controls. It has to be at a higher speed when it goes around B. Also, it's going to lose more energy when it goes up to B too, because it's got that other height. So it's not going to be C that controls. So it's going to be B that controls for that, right? Everybody see that? Okay. So that's not the answer, right? That's just what the minimum speed is. That's the minimum that they have to be going around at this point right here, right? If they go slower than that, they're going to drop, right? Or they're going to, if they're attached to the thing, if there's a positive connection there, which I would hope a roller coaster would have a positive connection just in case, so it doesn't just free. If there's a car, right, it would drop, but a roller coaster, I would hope that would control it, and hope that they're strapped in as well, right? But if it goes faster, then we would pick up a normal force there, and we're trying to solve it just right at the cusp of just when it makes it around that corner, right? So then now we would switch over to what? Work energy, right? We gotta go over to work energy at this point, because now I know the minimum velocity, but now what I'm after is this height right here, right? This height right here. How high does that need to be in order to get 6.64 at B? Okay, so let's do that. Now we do work energy. Work energy. So I always just do this T1 plus V1 plus work done from 1 to 2 is equal to T2 plus V2, right? Starting out at rest, kinetic energy 0, right? Potential energy, again, we'll come to that one. Work being done from 1 to 2, there's no other forces acting on it, there's no friction, stuff like that, so that guy's 0. Kinetic energy, there's going to be kinetic energy. Is there going to be potential energy? Depends, right? Depends on what we define as our, yeah.
Are you going to have it marked down as PE, KE instead of...
No. It'd be funny if I did that, though. Right? Just, oh, sorry, all wrong. It's supposed to be T here, not KE. That would be funny, though. All right. Gotcha. -1. Okay. So let's define our datums, right? Again, I usually like just to say, let's come in here and say y equals 0 down here. All right. There's going to be 0 right there. And then, so if I define y equals 0 at the bottom, then I'm going to have potential energy here, and I'll have potential energy here, right? If I do that, it's fine. I can do it that way. Or, I could say y0 is here, and then I'll only have potential energy at state 1. Either way, right? It ends up being, it's just the difference that matters. And if I put it, here and here. Well, the half will be on this side, half will be on this side. It's the difference that matters, right? So let's do it, right? So this is V1. Oh, this is MG Y1. All right, this is H. That's what we're after right there, right? H. What did I call it? Yeah, H is equal to 1/2 MV 2 squared. Oh, plus MG Y2. We'll call it Y2. MG Y2. Okay. Now put our values in here. So see how much these guys weigh. The passenger's 300 kilograms. 800 times 9.81 times H, what I'm after, is equal to 1/2 times 300 times V2. That's the V minimum we just solve for, 6.64. 6.64 quantity squared plus 300 times 9.81 times Y2. Now Y2 is 9. Right, the diameter of that thing is 9. So they'll be at a height of 9 when they go over there. Right? So the only unknown in that is H. Make sure I set that up correctly. 1 H squared plus 9.81 times 9. Yep. Okay. And this will give you, right, plug that sucker in your calculator or do 2 pages of algebra and then. Actually, that's easy. That algebra is easy. I hope that doesn't take you 2 pages of that algebra. 11.25 meters. Right. So that's the answer to the first part. Right. It has to be 11.25 meters in order to get that velocity as I go around. Did I do that right? Did the answer supposed to get? Okay. That's part 1. Part 1 was that. I think that's what worth the most points, right? Right. Part 2. Right? It says, what is the normal force at point B? 0, right? We designed it that way, right? We did it on purpose, right? We did it right here. We set that equal to 0 at point B. So that's it. Okay. Normal force. Ooh. Normal force is equal to 0. Okay. 3 says, part 3 says, starting at the height found in 1, what is the normal reaction on the cart when the cart is at sea? I'll tell you this, grading these things, the way that I have it, I try not to do this usually where you have to get the right answer and then all the other answers are based off of that answer, because that's just like if you make up one mistake at the beginning and then it just trickles through and then I have to go back and find like why did you get the wrong answers. I usually try to do it as best as possible, but I don't like it when I do that. But in this case, we do that, right? So it's based off of that original height, right? So this is something. It says, starting at the height found in 1, what is the normal reaction of the cart when the cart is at sea? So what are your thoughts there? How do we do that?
Start with another free body diagram.
Yeah, eventually. What else should I know before I even get to that, though? I should know what my velocity is when I get there. You're right. You could do a free body diagram, right? And you'd get there, but then you'd find out you needed VC. So you could do it either way, right? Absolutely. You could do it either way. And then, because then right after we find VC, then we'll do a free body diagram. So I just flip it. Either way you could do it. It just works like that. So how would I find VC? Work energy, right? We'll just do work energy. We'll go back to work energy. So we'll do, yep. So then I'm after VC, right? So then I'm going to go KE1. This is so much more work, right? No, I'm not doing it. I'm not doing it. I like my T's. Right. T1 plus B1 plus work done I'm going from 1. Yeah, I could do. Yeah, 1 to 3. I guess we'll call it 3 is equal to T3 plus V3. Right? And I want to point something out, right? I could go from, and this has happened on this problem in the past. I can go from A to C, or I can go from 1 and 2 and to 3, right? And I could skip what's happening in there. And the reason I get to is because energy is conserved, right? So the energy at 1 is going to be the same as the energy at 2, which is the same as the energy at 3. Right, so you don't have to do intermediate steps. I can go all the way from 1 to 3. Where I couldn't do that is if there was work being done between certain ones, right? Because then the energy is getting pulled out of the system and it isn't equal. You don't have a constant energy. But in this case, there's no work anywhere being done. So my energy at any point on here is the same, right? And so I can go from all the way up here to all the way down here. Right, and I've seen, when I did this problem originally, people were going from here down to here, then up to here, then down to here, then over to here, then up to here, and there was just so many steps along the way. But you don't have to do that. Energy is conserved around that whole system, and you can go all the way from A all the way to C, and that energy is conserved the whole way. So that's why I can go from 1 to 3 right there. It's because the same amount of energy, right? And so, like we said, at state 1, there's no kinetic energy. There is potential energy. There's no work being done, and then there is going to be potential energy and there will be kinetic energy at state 3, right? Because I've defined y equals 0 there, so there will be potential energy there. So at this point, start plugging in our values again. So this is going to be mass times gravity times that height, right, is equal to 1/2 mv3 squared plus mgh, mgy3. Right? And then I just plug in some values here. Let's do this. Let me go to room over here. So my mass here is my 300, what is the mass? 300 kilograms. 300 times 9.81 times the height that I found, 11.25. Equal to 1/2 times 300 times V3 squared plus, oh my gosh, I ran out of room. So I'm gonna do it there. Plus 300, sorry. 300 times 9.81, and that height now is gonna be 6 meters times 6. Right, and so V3 is equal to V3, or VC, I guess, which is the same as VC, is 10.15 meters per second. Okay, so when they get down to point C, when they get down to this point right here, they're going to be, and when they're at the top right there, they're going 10.15 meters per second. So they're going around there. Now, free body diagram. Back to that free body diagram to figure out what that rest is. I'm going to cram this up a little bit. A little bit more room. Okay. Now I got rid of the free body diagram, and I've got, and we kind of have it drawn before, but we're going to have a normal force. Oh, usually the blue. Normal force, and then I'm gonna have mass times gravity going this way. Right, so then I look at some of the forces in the R direction. Force in the R direction is equal to minus n, plus n, right? Because it's now R is going up. All right, so it's minus n minus mg is equal to negative mv squared over r. Right, that's what I need right there. And what I'm after is the normal force, right? That's what they asked for, is the normal force. So I'm after that normal force. So now I just plug in our values. Negative normal force is equal to minus, minus 300 times 9.81 is equal to negative 300 times the velocity I just found, which is 10.15 squared. And I divide it by the radius in this case, which would be 3. And you solve for that normal force. And normal force is equal to 7,359.25 newtons. Is that a lot? I have no idea. It's newtons. Who cares? Right? Who knows? Who knows what a newton is? Is that a lot of newtons? 7,000 newtons? A few newtons? Okay. I don't know what that means either. But I got no feel for it. I got no feel. What is a newton in a pound? What's that? Oh, is that true?
Yeah, so it's like 73.
Did you guys know that?
It's like a tenth of a kilogram.
Because a newton hit him in the head with the apple. That's how it originally came from, right? That's what it was. The average weight of an apple. That's actually interesting. I did not know this. Okay. I did not know this. That's great. That's good to know. Yeah. Okay. Are we, everybody cool, right? That's not bad. All right. Okay, just it keeps going, right? I was getting crazy this year. What else have we got going on? So 4 here, right, says, what if 4 says, starting at the height found in 1, how many G's of acceleration do the passengers experience at point C, right? So this is just acceleration, and I have an equation for acceleration. AR is just equal to V, this would be V, what we're calling V3. V3 squared over R. And that's the acceleration in the radial direction, right? That's all it is at this point, right? And so this, you just plug in all the values that we have here. Right, this is equal to V3 is 10.15 squared all over 3. And that you get 17.99 meters per second. And then that in terms of G, you just divide by 9.81. Nope, I did that wrong. That's not equal to that. That is not equal to that. This is equal to, that's actually equal to 34.34 meters per second squared. Divide by 9.81, we get 3.5 Gs. That, I have a feel for that. 3.5 Gs of, right? Can you survive 3.5 Gs? Yeah, you bet. For that short period of time, you bet. Just, yeah, you could survive that. You can survive, for a short period of time, you could survive a lot of Gs. It's prolonged that gets you. We'll watch a video, one of these days, we'll watch a video of people going through G-lock. Have you ever seen somebody go through G-lock where they get whipping around and then they pass out? It's pretty funny. Okay, last step, 5. Man, I really stuck it to him this year, right? It says, oh, okay, wow, that was extra credit. The extra credit, that's why I did it. Okay, what is the maximum height so that Tom and Calvin do not experience more than 11 Gs of acceleration in the loop, right? So 11 Gs. So we go back to this. AR is equal to 11 Gs times 9.81. That is going to be equal to V squared over R. Right? I guess at this point, which loop do you think they're going to feel the most G's? Tighter one, right? C. The tighter one is where they're going to feel the most G's. So at that point, that'll be a 3 right there. This guy here will be 3. Right? That'll be 3. And then what you get is, now the velocity. This velocity ends up being equal to 17.99 meters per second. Okay, so that's the velocity. If they're traveling around 17.99 meters per second, they will feel 11 Gs of force when they go around that. Can you survive 11 Gs of force? Yes. Would it be pleasant? Not for me. I wouldn't want to do that. But I'm sure it's just for a couple of seconds, just milliseconds even, you'd feel that 11 Gs, and then you get butterflies and all that. Okay, So at this point right here, this is where I messed up, right? Where are you gonna feel the most G's when you go around that corner? Right here. Right when it starts the jump. Because let's see, let me think what I'm thinking here. Coming around, you're gonna feel it up here too. But see if you, oh, that's right. See, okay. This is what I'm thinking. So we're trying to find what is the maximum height so the atomic calculus. If I do that, if I said it was at point C that they felt that, right? Is point C going faster or slower than the bottom? It's gonna go slower than the bottom. So if I set VC equal to, if I had set VC equal to 17.99 up at the top right here, when they were down here at the bottom, right before they went around that corner, they would be feeling more than 11 G's of force. Okay, yeah, right? They'd be feeling more. And so it's gonna be right here, right when they start taking that whip up is where they're gonna feel 11 G's. If you said it was right here, then they would be more than 11 G's at the bottom. And so it has to be that. And so that's where that number came from. So then you just go back to that. Man, don't worry, it isn't gonna be this long. I won't keep asking questions like this. 9.81 times H is equal to 1/2. I crossed the mass out of there. Mass, V squared. All right, these guys go away. Then that height that you solve for. And then this guy goes right there. All right, and that height you get is 16.5. Right. And if you went higher than that, then you would feel more than 11 G's. I would assume, I don't know. I wonder if the designers of roller coasters do this. Maybe initially for some rough calcs, and I would assume there's some sort of finite element analysis that models it better. I'm not sure. Any questions about that one? Right? That was a little long, right? There's too many steps. I don't think I would give you something like this in 25 minutes. But you should definitely know how to do it, right? I mean, it's not too difficult. Okay, this guy right here. This is similar to a problem we've done before. Tom and Calvin again, right? You're kind of loading them up like a pinball machine, right? They pull them back at a certain distance, right? And have some energy stored in that spring. We release it. Whew, they slide across this thing. A slams into B. Tom runs into Calvin. The two then stick together because there's little hooks right here, and then the two travel up under this little decelerator. And I think we're asked to find the height that Tom and Calvin ascend together after that collision, right? So this is a multi-step problem, right? We're gonna go. I guess I got them already labeled here. Go 1 to 2. 2 to 3 is going to be collision, and 3 to 4 is going to be work energy. So we're going to work energy from here to here. Then we're going to go collision from 2 to 3, and then we'll go 3 to 4 here. You cannot say energy from here to here is the same, because it is not. If you say that is the same from the beginning, I love those ones because I just go 0 and I move on, right? So it's easy to grade. It's super easy to grade. So do please do that. Do please do that so that it's easier for me to grade. Or get the exact right answer. I like those ones too, right? And in fact, I like those ones better, right? Because I'm testing myself too a little bit, right? Like, how well did I teach you, right? How well did I teach you? And sometimes I am very disappointed in myself. But sometimes I'm just, God damn it, I failed. Okay, so let's do that. So you just step through this problem, right? This one's nice because it's going in the same order as chronologically, right? I know what's happening at 1, and I'm trying to find what's happening at 4. Sometimes you do it backwards, right? And so 1 to 2. Right. So we are going T1 plus V1 plus work being done from 1 to 2 equal to T2 plus V2, right? I have to do the state right because there's friction, right? Isn't there friction? Is there friction?
No.
Oh, neglect friction. Keep it tight. Oh. Okay. All right. Fair enough. Okay. All right. Okay. No friction. Yeah. Okay. We're okay. Yeah. All right. I'm back to normal. All right. Okay. So, all right. No potential. Oh, yeah. Sorry. Any kinetic energy at the beginning? No. Right? Because he's starting at rest. Right? How about work being done from 1 to 2? Nope. That was nice. I said we're going to neglect friction. So there's no other forces acting on here. There's a normal force, but that doesn't do work. Right? There's no friction that's acting against motion, so we're good. Is there a potential energy at state 2? No, right? There's not, because there's no change in height at that point. And so that's what I'm doing. I'm doing potential energy at state 1, and then I'm going to kinetic energy at state 2. Right? So potential energy at state 1 is 1/2 Ks squared, and that's going to be equal to 1/2 mv. Ooh, let's put a subscript on that. I don't know who's flying there. Tom is first. MT v2 squared. Right? Plug in our values. 1/2. Our K is given to us is 5,000 Newton meters. 5,000 times, they give us initial displacement of the spring of being 3 meters, that's 3 squared, and then that over 1/2 mass of Tom is 100 with the cart, and that's V2 squared. Okay. It's nice, the only thing unknown there is what V2 is, so I can solve V2 ends up being equal to 21.21 meters per second. So that's how fast Tom is going when he slams into Calvin, okay? So now there's a collision that's taken place. When there's that collision, there's deformation, there's sound, there's maybe an explosion of some sort. There's a collision that happens, and there's gonna be energy lost. But no matter how much energy is lost, momentum is conserved. This blows my mind that works, but it does, right? That no matter what, momentum is conserved. So in that case, we're going linear momentum. This is 2 to 3. Right? That's going to be impulse momentum. It's going to say mass of Tom times the velocity of Tom plus the mass of Calvin times the velocity of Calvin. 1 or 2 here, but that's going to be 0 in a second, is equal to the mass of Tom plus the mass of Calvin times the velocity at 3. Right? Because they're sticking together. They're both going under the same. They're stuck together, and so that both of them are going to be going to the same velocity. They're going to have the same velocity afterwards, right? So Calvin has 0 velocity at the beginning, so that guy's 0. So we're just going momentum of Tom into momentum of Tom and Calvin, right? So Tom's mass is 100. He's going 21.21 meters per second. The 2 of them together is 200, and then it's going to have velocity 3 afterwards, right? And we solve for V3. V3 is equal to 10.61 meters per second. Okay? So now we know how fast they're going afterwards, right? And that energy is not the same before or after. Before and after. Okay? Now we go 3 to 4. Now we're back into work energy. 3 to 4. 3 to 4. Okay. So now I go T3 plus V3 plus work being done from 2 to 3, or 3 to 4. 3 to 4 is equal to T4 plus V4. Okay. Kinetic energy at state 3, you bet. Potential energy at state 3, no. Work being done, no. Kinetic energy at state 4, no, because it's coming to a rest. Right, boom. These are nice because there's only a couple terms here going on. Right, so we got 1/2. We got 1/2 mass of Tom and Calvin, MT plus MC, because they're together, times V3 squared is equal to mass of Tom plus mass of Calvin times G times H. Right? Right. Yep. There you go. These, I mean, if you want, you boop. Right? These guys are canceling. Boop. Right? And you could solve for the velocity. G's 9.81. That velocity here. All right, let's put it in. I'll be complete here. 1 half V3 10.61 squared is equal to 9.81 times H. And H is the unknown here. My H is equal to 5.73 meters. That's the answer we're after, right? That's what they asked us, is how high will they go? Again, not bad. You know, and again, I have to stress this. If you have time, I understand when you're answering the questions and that you get, things get out of hand and you spend, and then you just throw shit down. Okay, I get it, and I'll do my best, but I'll be grumpy when I do it. If you laid out a problem like this, you're just like, yeah, here we go. This to this, this to this, this to this, and you cross out all the stuff. It's so easy to grade because then I can go through and be like, oh, look at that. They accidentally put in, one mass instead of two masses or something like that. It's easy to grade. It's nice and nice and laid out. And then if you're using your calculator, again, totally fine. Please do. Please use your calculator. But when you do it, get to this point. Get to this point where I can see what it was that you put in there, and then I can figure out if it was right or wrong, and like what was it? Did you just fat finger it, right? Did you just hit in your calculator like this, right? Just big old fat fingers, just boo boo boo, right? Is that what it was? You wrote the right equation, right? Or was it, sometimes we just, here you go, maybe even not get to this step, and then here you go, and then there's an answer, and I don't know what you did wrong, right? I have no idea what you did wrong. My favorite thing to write on a test is when you have this right thing, and then I say, I remember the first time I tried to use a calculator. That's right. That's my favorite thing to type out. I remember the first time I tried to use a calculator, right? Or fat finger. Oh, you fat fingered it, right? Okay. And I don't know if you picked up on this. What I really stress in this class is setting up the problems. Clean, setting them up. The right answer is such a small part of it. If you set up everything perfectly correct and then you get the wrong answer, that's a small deduction, right? I only deduct small for fat fingers, right? It'd be a different story if you were launching something to the moon or Mars or something and you fat finger it. Like, that's a big deal. Your dynamics test and under pressure with an hour, 50 minutes to go, right? Okay, I get it, right? I get it. I'm not going to hit you too bad, right? I'm not going to hit you too bad. I may make fun of you, but I won't actually deduct too much. Okay? All right, second part of the problem. Part 2, how much energy was lost to the collision? Any thoughts on that one? How you would get that?
Find the energy before.
Yeah.
And find the energy after.
Yeah. Right? Find the energy before and energy afterwards. I could do, right, when I'm talking energy, right, what's the energy at state 1 compared to the energy at state 2? They're the same. So I could go, what's the energy at state 1 minus the energy at state 3? I could do the energy at state 2 minus the energy at state 3, right? All the energy before versus the energy afterwards, right? Right? I could go the energy here compared to the energy here. Huh? I could. Because the energy after the collision is the same, right? Is constant. Okay? So what did I do? I did E2. Let's do it this way. Let's say E2 minus E3 would be the energy lost. Right? Or E3 minus E2, positive versus negative. I'm going to go, well, let's not do that. I don't want 2 or 3. Let's go 1 to 4. Let's just do it. Let's do it. Let's be crazy. 1 to 4. Right? They won't be the same. Again, don't say the energy is the same all the way across. So I got 1/2 K S1 squared minus mg H. Right? And so here, just to finish it out, that's 3, what was it? 5,000, that's 5,000. 5,000 times 3 meters squared minus mass, it would be 200. Is it 200? Two of them, yeah, 200 times 9.81 times that H, 5.73. Right. And then 11,250. Right. The units there would be Newton meters or joules. Whoa. So that's that energy loss. Isn't that crazy that you could do that? You could figure out how much energy you post-calculate what the energy was lost. Right. Last little step, extra credit, was how much work. We haven't done that. I don't think we've done this. How much? What was the force be if the time that it took to transfer that force was 0.2 seconds? Right. And again, I don't think we've done this, and this is why this was extra credit, just to see. So we had this equation somewhere in there. We derived this F dt, the integral of F dt, which is an impulse, right? A force acting over time causes a change in momentum. mv2 minus mv3. Actually, this should be probably, actually it should be the other way. It should be v3 minus mv2. Doesn't really matter. I didn't take for, it just throws off signs if you do it, right? And so if the force is constant, so we're trying to find the average force. I don't know if I said the average force, but it would be the average force. We assume that F is constant, then this would just be F times delta T is equal to mass times the velocity of 3 minus mass as a velocity of 2, right? And so this is just one body, by the way, right? This is, it takes a little bit of, this is, this guy rams into this guy, right? And imparts a force. Right? And then this guy then also imparts a force. So you could do either one. You can actually, you could see what does Tom do to Calvin and what does Calvin do to Tom. And so when you're looking at this equation right here, this is just one body, right? It's what does this force do to this guy, and what does this force do to this guy? So in the masses that you're using over here is just one of them, right? It's just 100, right? So this guy, this force times 0.2 is equal to the 100. And so if we did, Calvin was at rest, right? So this part right here was 0. Right? This guy right here was 0 because Calvin was at rest at the beginning. And so this guy would just be 100 times, but he went from 0 to, what was the velocity afterwards? The velocity after the collision was 10.61. Right, and I think we get here, that force then ends up being equal to 5303.3 newtons is how big that force ends up being. And it's a big force, I think. I mean, I don't know what a newton is. 5,303 apples, right? 5,303 apples hitting that thing. Okay, that was Tom hitting. That's what Tom did to Calvin is the force. You could also do it the other way if you wanted. What did Calvin do to Tom? And so you could go same deal. You got to flip it, and we should get the same answer. F times 0.2 is equal to, how fast was Calvin going to begin with? He was going 100 times 21.12, right? Minus 100 times 10.61, and I think you should get the same thing, right? Actually, you should get it opposite. You should get F equals negative 5303 newtons. Right? You do either one. Right, because one affects one and the other one affects the other, and they should be equal and opposite when calculated. Right? Like I said, we didn't do this. I don't think we ever did. We wrote the equation before, but that's why I was like, actually, could you come up with this? Did I do? I wasn't done. What? What did I do?
Those two be switched.
Oh yeah, probably.
If we're looking for
3. Yeah. I wasn't done yet. I was gonna say this should be a positive and this should be a negative. Right? there you go. Yeah, it's I didn't dock for signs, but you're exactly right. It should be the 3 minus the 2, and so it should have been. I should have had that on the left and the other one on the right. Yep, absolutely. Because it should be negative. Because one should come out going that way, one should come out that way. Yes.
Is that 0.2 given in the problem?
Yeah, the 0.2 was given. It said, what is the average force accelerated atomic scale during the impact if the impact occurred over 0.2 seconds? Right, and it was average. You have to say there was average too. Okay? Hopefully you feel confident because it's tomorrow morning, right? It's tomorrow morning. It's going down, right? You have any other questions? Yes.
Just with B3, 10.6, that was the velocity when, is that the velocity when both?
Oh shit, what did I do?
No.
Oh yeah, I did. Okay. The 10.6 is the 2 after they're stuck together.
Yeah. So can we use it? So when we're using that to find what was that last bar? The force.
Yeah. So that was.
100 kilos.
So this guy was going. Tom was going 21.21, but after they stuck together, he was going 10.61.
Yeah.
Okay. But what did you?
I was just confused. I thought you would add the masses together. For the
No, you would think that, but we're trying to solve the problem. You're exactly right, but we're trying to find the problem of what does one, like when they hit each other, this guy pushes on that guy and this guy pushes on that guy, right? And so it's their individual. There's individual ones, right?
Yeah.
Yep.
Okay, that makes sense.
Yep. And that's why the first one we said it was 0 because Calvin wasn't moving at all, and he went from 0 to 10.61, and so that's why it was just 1 term. The other one got 2 terms because Tom went from 21 point whatever to 10.61. Slowed down. Okay.
Yeah, that makes sense.
Yeah. Cool. Any other questions? Good to go.
Running manager for this one, would it be F or F average?
I don't know. Yeah, if you got to there, man, I'm celebrating, and this is great. Yeah. But technically, it would be the average, right? Because when I said F times 0.2, that's making the assumption that F is constant and comes out of that integral. And so, yeah. Otherwise, you couldn't do it. Yeah. But it probably wouldn't be average either, right? It would change. Yeah, it would probably start out low and ramp up. So, cool. All right. Good luck. See you tomorrow morning. Half of you.